Hello, today we will solve a problem on static equilibrium and explore an interesting question. To determine the location of his center of mass, the student lies on a light board supported by two scales placed 2.5 meters apart. In the diagram, we have shown the person's position. The left scale reads 290 newtons, which is force F1. The right scale reads 122 newtons, which is force F2. Question: find the mass of the student, and find the distance from the student's head to their center of mass. In this problem, it is clear that we will rely on the law of equilibrium of a rigid body from the perspective of the moments of forces acting on this object. And therefore, let's identify the forces acting on the board as a whole. In this case, we have two forces that arise from the weights. These are forces F1 and F2. In fact, this is nothing more than the reaction of the support. And why is the center of mass being discussed here? Meaning we imagine a person pressing on this board at the appropriate point. So in this case, specifically, here we will mark the position of the center of mass as point C and acts according to the weight of this person. Now our task is to calculate the necessary parameters. First, we will find the mass of this student. For this, we have the total force with which the student acts on these scales. According to the problem's condition, the board is very light, so we do not consider it in the overall weight of the system. Then it turns out that the weight of this person will be counterbalanced by these two forces acting vertically upwards. And also weight is nothing more than the product of a person's mass and the acceleration due to gravity. From this, we can find the mass of the given student. The sum of the two forces is divided by the acceleration due to gravity, and we obtain the expression. And approximately, based on the mass value, we get an answer of 42 kilograms. Overall, it's quite a realistic answer for a school student. Next, we will now calculate the center of mass position for this person. For this, we use point C as the reference point around which the object will rotate or attempts to rotate will be made. In this case, the gravitational force of the object passes through point C, so it does not create any rotational moment. However, two forces, F1 and F2, do create rotational moments. Each of them has its own lever arm. Let's illustrate these arms in the diagram. The distance for the first force, its lever arm, is precisely the magnitude of the position of the center of mass relative to the head. And accordingly, the second remaining distance will be the distance equal to the length of the board minus the given distance to the center of mass. Then it turns out that the two forces creating two moments must compensate each other. And thus it turns out that the moment of force F1 is the product of this force and its lever arm will be equal to F2 times the lever arm of this force. Accordingly, the lever arm of this force is the distance from point C to of this end of the board. And this value will be equal to the difference between the entire length of the board and the arm of the first force, that is LXC. Well, and now from here we need to express the coordinate of the center of mass XC. What we will do for this: we will expand the brackets on the right side by multiplying F2 by each term inside the brackets. And now all that's left is to gather all the terms with XC on one side, and let's factor out XC right away. Then inside the parentheses we'll have this sum of forces. And outside the parentheses we have directly XC. On the right side remains the passage of F2 onto L. Nothing changes here. And now from here we can easily find the position of the center of mass of a person. So the formula is ready. All that's left is to place numerical value. So F2 is 122 newtons. 2.5 meters. And here, the sum of two forces. After the calculation, we get the answer, 0.74 meters. This will be the distance to the center of mass of this person. Thus, the problem of the statics of a rigid body is considered, meaning we can also use Newton's first law, which means for this we must understand that when a body is in equilibrium, the total sum of forces is zero, meaning they cancel each other out. And from another perspective, the absence of rotation also indicates the balancing of these forces moments. That is, here we immediately applied two conditions of equilibrium for a solid. With that, I bid you farewell, and we'll see each other in our next sessions. Goodbye.